Welcome to the PDI Debug Utility Overview Tech module. Before diving into the PDI Debug utility, let's briefly revisit the notion of Programmable Device Image, PDI. The PDI file contains the device programming data, which is similar to the bitstreams file from the previous architecture. As you know, the AMD Versal device is composed of a number of highly coupled configurable blocks. These blocks, such as the NOC, AI engine, PL, and SIPs, which itself has different domains, LPD and FPD, all need to be configured at boot using the respective configuration binaries called Configuration Data Object, CDO. All of these configuration binaries, CDO, are packaged into a single container binary boot image file. This binary boot image for the Versal device is called a PDI, which is an AMD file format to boot and configure the Versal adaptive SoC. Along with the configuration binaries and bitstream, a PDI file may contain multiple partitions, including the bootloaders, firmware, and user applications, which are inessential to boot and configure the Versal device. The PDI data is specific to the design requirements. The Versal PDI boot image is processed by the Platform Loader and Manager, PLM, as part of the Versal device's boot process or partial configuration process. PLM plays a central part in overseeing the loading of firmware and bitstream and helping ensure a smooth transition to user applications. Once you generate the PDI file, next you will proceed with programming the Versal device. When programming an AMD Versal device, you might encounter programming errors. These errors can be reported by the device's boot ROM or might come from the Platform Loader and Manager, PLM, software. Understanding and analyzing these boot errors can be challenging as they are encoded and might require reading additional registers to identify the root issue. In the Vivado 2024.2 release, a new utility called PDI Debug has been introduced to help with debugging. The PDI Debug utility assists with generating error reports, analyzing and providing debugging suggestions for errors that occur in the PLM and boot ROM, as well as with JTAG and error status registers. It can also be used for programming the PDI and analyzing errors upon failure. Some use cases for the PDI Debug utility include decoding a PLM error, decoding a ROM error, analyzing errors from a log file with or without a PDI file, analyzing errors from the connected hardware, programming the PDI, and analyzing errors upon failure. Here's the general syntax for using the PDI debug util commands. The available options are as shown here. The command value can be one of the following: analyze, to analyze the error log and the device status; decode, to decode one or more ROM or PLM errors; program, to program the device and analyze any errors afterwards. Each command value takes different arguments as shown here. For more details, see the Vivado Design Suite Programming and Debugging User Guide. The most basic feature of PDI Debug Util is decoding a PDI error. When a boot configuration error occurs, you can obtain the PDI error information either using a JTAG or from the Versal device's UART output. Here's an example of a PDI log output for a Versal device. The PDI log output for a Versal device generates the PLM error status. Call the PDI debug util to find out what this error means. This command produces an output as shown here. The PLM error status is composed of a PLM major error and a PLM minor error as shown here. The combination of these two errors helps narrow down the specific error detected during boot. The analyze log subcommand analyzes the PDI configuration error logs. Here is an example of running the PDI debug util analyze log subcommand, which targets an XCVC1902 device belonging to the Versal architecture. The output of this example is shown here. In this case, the error from the log indicates an ID code mismatch. This log was generated when attempting to boot using the designtop.pdi on an XCVM1802. Because this PDI is not compatible with the device, the boot log shows that the configuration is terminated with the generated error status. This example shows that with a PDI log, the analyze log command can read and process errors contained in the file. This command is useful when working with remote situations where the Versal device is not directly accessible for debugging. The list targets subcommand lists the targets detected on a JTAG chain. In this example, PDI debug util list targets subcommand is used to determine the target index of the remotely connected device to the host named myHost. Running this command will show all the targets on the system. The output indicates that the XCVM1802 device is located at target index 0. In the case of longer JTAG scan chains, all detected devices on the chain are displayed. This information is used to pass in the target index of the Analyze Hardware or Program subcommand. The Analyze Hardware subcommand analyzes configuration error remotely via a JTAG interface. Shown here is an example of the Analyze Hardware subcommand. In this example, the design has been configured with a PDI intended for the XCVC1902 device. However, it is anticipated to fail as the part on the board is XCVM1802. In this scenario, the PDI debug util is used to connect to host myHost to analyze a Versal device. Also, the T flag is set with a value of 0. It is noteworthy that for this specific JTAG chain where the target device, XCVM1802, is connected, the T option could have been omitted because the default target index value is 0. Nevertheless, it was incorporated to showcase the use of the target index option. As shown here, you will get an ID code mismatch as an error description. The Analyze Hardware subcommand requires no details about the target device. This is because the Analyze Hardware subcommand automatically detects the device details based on the selected target index. Additionally, the subcommand takes care of reading the log and providing additional status information, so you do not need to supply a log directly. If more details were required to analyze this type of error, the command would have displayed additional register information related to the issue. This command is particularly useful in cases where a system has unsuccessfully attempted to boot, or in DFX scenarios where a post-boot image fails to configure. The program subcommand configures and analyzes errors remotely via a JTAG interface. Let's take an example which is similar to the one used for the Analyze Hardware subcommand, where a PDI is programmed on the wrong targeted device. Here is the command used for this example, and the output can be seen below. In this output, the program subcommand starts by configuring the device with the PDI file. The programming status denotes the progress. In this case, it ceases at 21% due to a reported error. The error status is presented, initiating the analysis process. The analysis involves deciphering the error and subsequently concluding the analysis. Let's summarize this tech module. PDI debug utility is a key for error-free boot configuration that assists with generating error reports, analyzing, and providing debugging suggestions.